Today we are gonna continue the kinematics of particle. We'll take a new application, a projectile application. First, we'd like to explain the meaning of a projectile. What is the meaning of a projectile? Suppose that we have an aircraft flying at a certain altitude, 300 feet, with a constant speed of 180 miles per hour. And at a certain time, the pilot dropped a particle or a specific mass, the blue one, at a certain time. This mass directly will take the speed of the aircraft as a horizontal speed of it. It means the horizontal speed of this dropped particle will equal to the speed of the aircraft directly. The initial vertical speed of this particle will equal to 0, as long as we didn't mention that we push or add any initial velocity to this particle in the vertical direction. Okay, this particle consequently will perform a path shown on the figure. That means this particle will perform a general plane motion. That means this plane motion will have two components, two velocity components, two displacement components. We have a vertical displacement and we have a horizontal displacement. The same, we have a vertical velocity at any time t and a horizontal velocity at any time t. At any time t on this path, we have both a horizontal velocity and a vertical velocity. Something like this. Horizontal velocity and a vertical velocity. So, how we can describe the displacements, the velocities of this particle along this path? Let's start with a simple falling particle to the ground. Suppose that we have a particle like this, drop downward to the ground. We have altitude h, and we'll take our reference coordinate in this direction. This is a positive x, this is a positive y, this is the origin. And we can assume initial vertical velocity v0 y for this particle. When we drop this particle, it will be subjected to the gravitational acceleration, to the gravity. So, the gravitational acceleration, or g, the gravity, equal to minus 9.8 meter per second square. In other words, equal to minus 32 feet per second square. That's the gravity, the gravitational acceleration. So, how we can describe the displacement and the velocity in the vertical direction? We know that delta V over delta T equal to the acceleration, the first differentiation of the velocity with respect to time equal to the acceleration. We can replace the acceleration by G, the gravitational acceleration. That's practical. Consequently, we can, by integration, we can get the final velocity or the vertical velocity of this particle at any time t equal to the initial vertical velocity v0 y plus g times t. That is a popular equation that describes the vertical velocity or the final velocity of the particle at any time t in terms of time. take into your consideration that g is minus 9.8 meter per second or minus 32 feet per second square. Minus 9.8 meter per second square or minus 32 feet per second square. The same way you can write delta y over delta t. This is vertical displacement in this direction equal to the velocity y in the vertical. We are speaking about the vertical displacements and the vertical velocity in this example. Consequently, by integration we can get that y equal to y naught, the initial displacement, plus the initial vertical velocity v naught y times t plus half g times t square. This also is a popular equation that describe the vertical displacement in terms of time t. As long as the starting point is the same point of the reference coordinate, as long as our starting point on the reference coordinate origin, we can eliminate this y naught by 0. As long as we mention that this particle was dropped, only dropped, without any additional initial vertical velocities, we can also eliminate or substitute with 0 instead of this v naught y. Anyway, we have two equations that describe the vertical velocity, the vertical displacement of this particle, of this falling particle to the ground. Okay, now we are dealing with projectile. What is the difference between a projectile and this case? A projectile, as we said here, has two components, two velocity components, two displacement components. Also, we will take our reference coordinate at the starting point. Most of the cases we usually take our starting point on the origin of our reference coordinate. That means the initial displacement will equal to 0. Now we have a projectile that is performing a general plane motion or is performing this path. Anyway, we have a vertical displacement, we have a horizontal displacement. And as we said before, at any time t, we have here a vertical displacement and a horizontal corresponding displacement. And at any time t, we have a resultant velocity that is composed of two velocity components, one in the horizontal direction, one in the vertical direction. So how we can apply this equation in our projectile application? We can divide our projectile application into two directions, into two motions. Y direction referring to this case, we can write that the vertical velocity of this particle equal to the initial vertical velocity plus the gravitational acceleration times t, and the vertical displacement y equal to the initial displacement y naught plus the initial vertical velocity v naught y times t plus half g times t squared, as we mentioned before. This for y direction. We can add also x direction, as we have general plane motion. I have two components for displacement, for velocities. As long as we have no resistance, we have no drag against the flying object or against our flying projectile. That means the horizontal speed of our particle is constant. That means V naught x equal to Vfx. The initial horizontal speed equal to the final horizontal speed equal to Vx. The horizontal speed of a projectile or our particle is constant as long as we have no resistance, we have no drag opposing the object. So we can write directly x equal to the horizontal displacement, equal to x naught plus Vx, the constant horizontal speed of the projectile, times t. It's the simplest equation of the horizontal displacement. As long as we take our starting point directly on the origin of the reference coordinate, as we said before, our starting point is the same as the origin of the reference coordinate, so we can eliminate x naught, we can eliminate y naught. As long as the problem mentions that the object or the projectile dropped, so we can eliminate this initial vertical velocity. Sometimes we can change all these constants, sometimes we can eliminate them according to the according to the state of the problem. Okay, this general view about the projectile. Let us apply this equation on our application shown on the whiteboard. We have an aircraft flying with 180 miles per hour at a constant altitude 300 feet. We have fires there in the jungle. We have a burning jungle here. We need to know when, at which distance d, the pilot of this aircraft can drop the required quantity of water to reach point P to extinguish this burning jungle. Again, at which distance before the jungle, before the burning jungle, the pilot has to drop the quantity of the water to reach to the beginning of the jungle, beginning of the fire at point P. Simply, the aircraft is flying with 180 miles per hour and on a constant speed, on a constant altitude 300 feet. We need to calculate the distance d that confirm the quantity of water, that confirm the particle reaching point P. How we can apply our equations? We start with y direction. We have the vertical displacement y equal to the initial displacement y naught plus the initial vertical velocity v naught y plus half g time squared. As long as our starting point on the same point of the reference coordinate origin, we can eliminate y not equal or put 0 instead. As long as the problem mentions that the pilot dropped this quantity of water, this particle, so we can eliminate also the initial vertical velocity. That means y equal to half gt squared. Y representing the final altitude after the particle reach point P from point A to point B. It falls 300 feet and it covers distance d. So according to our reference coordinate, this altitude will be in the negative area. We can substitute with negative 300 equal to half minus 32 times t squared. We are using feet per second square as a whole problem using the feet and seconds and so on. From this equation we can calculate time t equal to 4.33 seconds. That means this particle or this quantity of water will take 4.33 seconds to reach point B from point A. That means it will fall down 300 feet at this time and it will cover distance d at this time. In x direction, can use our simple formula, x equal to x naught plus vx times t. The same as long as we use our starting point at the same point of our reference coordinate origin, so we can eliminate x naught. That means x, the final horizontal displacement d, final horizontal displacement d, equal to the horizontal velocity of the particle times t. Directly we can write d equal to 180 miles per hour. By conversion, we can multiply times 1.47 to convert 1 miles per hour into feet per second times 4.33 seconds. The required time that the particle needs to reach point P from point A and to fall down 300 feet in the vertical direction and to cover distance d in the horizontal direction. Directly you can calculate d equal to 1140 feet. That means this d equal to 1140 feet, and this altitude, as we know, is 300 feet. This particle or this quantity of water will reach point P from point 1 in 4.33 seconds, falling down 300 feet and covering 1140 feet in the horizontal direction as the final point. We can apply Matlab software on this application to determine each point on this path, each point on this path, also to calculate the tangent angle at any point, to determine or to show the angle of the resultant velocity at any time t, at any time t. We'll use Matlab code to try to investigate and to analyze some other points and some other relationships between the tangent angle and the velocity components and the displacement components. Let us try using Matlab and apply Matlab code and Matlab capabilities upon this application.
Here we are. Let's resolve the last projectile application. At the beginning, we need to have a glance over the Matlab windows. Start with the current folder window. Here you can find all the files and folder inside the current folder. Here is the workspace window that includes all the current variables with the relevant dimension for each variable. Here is the command history window that stores all the previous commands or previous statements, so you can recall any statement you'd like instead of writing any statement from the beginning. The main window, we call it command window, where you can write the required code or statement to perform the required or this specific task. Let's start with time t. Time t, we have defined time t as in range from 0 up to 4.5 seconds. That's the range of time t with increment of 0.01 or a step of 0.01. That means we have 451 element inside this variable t. You can recognize also in workspace time t is one row times 451 columns or 451 elements. Let's move down and activate this statement, which is the initial vertical displacement, and this one is the initial horizontal displacement, which equals to 180 mile per hour times 1.47. 1.47 is the conversion factor to convert mile per hour into feet per second. Now we are gonna recall all the basic equations that we have used in the last session. This one representing the vertical displacement of our projectile. You may recognize a little bit difference here. You can see y of k, t of k, t of k. Instead of writing y or t, the reason for that is that Matlab actually deals with arrays instead of single values. So when we represent a variable, we represent this variable in a form of array. Also, we write this equation inside a for loop to recalculate the equation several times according to time t. Let's move down this equation in representing the horizontal displacement of our projectile, and this one representing the horizontal velocity, this one representing the vertical velocity, and the last one representing the theta or the tangent angle at any point on the path shown in last session on the whiteboard. At any point we can get the tangent angle from this equation. Now we going to see the plot after we discuss the plot statement. Here is the plot statement. We have here 4 elements. If we are going to represent a curve or a correlation between two variables, y and x, we need 2 elements, y and x, like this, y and x, to represent a single curve. But we have here 4 elements because we are going to represent 2 curves, 2 correlations. Each 2 elements represent the x-axis and the y-axis. For example, x and y represent the vertical displacement with respect to the horizontal displacement, y and x. Here, we represent the tangent angle at any point on the flight path with respect to the displacement, horizontal displacement. Now, we move to the plot. You can see here the x-axis that is representing the horizontal displacement in feet, and the y-axis that is representing the vertical displacement in feet and tangent angle. The blue curve is the flight path of our projectile. You can use the data cursor to locate any point on this curve to get the horizontal and vertical displacements. If we are going to verify our solution or our result from the last session, we remember that we have at 300 feet vertical displacement downward, we have a horizontal displacement of 1,140 feet. That's true according to this point. That means the solution we got last session was correct. 300 feet vertical displacement downward, and only 1,140 feet for the corresponding horizontal displacement. If we are going to discuss this red curve, this red curve is representing the tangent angle. The tangent angle of this path at any point. Any point here, you can imagine a tangent at any point, and you can recognize that this tangent has a negative angle as this angle is located in the second quarter on the Cartesian coordinate. So we expect a negative angle of any tangent on this path and a negative slope also on at any point of this path. That's why we have all the values on red curve are negative. As we said, any tangent here at any point has a negative slope and a negative angle. You can recognize that all values also here on red curve are negative. But if we are going to calculate the impact angle at the end, at this displacement at 300 feet vertical displacement downward and 1140 feet horizontal displacement to the right, if we are going to calculate or determine the impact or the corresponding impact angle at this point, we can locate the corresponding point here on the red curve, and directly we can get the angle of the impact equals to 27.6 degree. That means at the end, when the projectile hits the ground after 300 feet downwards in vertical direction and 1140 feet in the horizontal direction, the impact will have an angle of 27.6 degree. Representing correlations and equations in this way by using code and Matlab window and using this kind of plots, we can get several conclusions. We can get several correlations between variables. We can have more than one solution. We